Good evening, everybody. My name is Ron Winward. I'm Security Evangelist for the Americas for Radware. I've been at Radware about 2 years, and prior to that, spent a long time with my friend Alex at Server Central. And actually, Alex and I go back way before that, many, many years in networking. I want to just touch on one quick point about Chris's talk. Will we be replaced by scripts? I also believe that the answer is yes. There is a website at the BBC that says, will I be replaced by a robot? And you can put your job in, and when you put in IT technician, the answer is very likely that you're going to be replaced by a robot. So, but there's not to get too far off topic here, there's some reasons that we think for that, and they are, like, if I can rely on automation for something in my network, right? If it's provisioning, if it's detection, if it's SIM data, that kind of thing, that frees up a lot of those human cycles that we can spend a lot more time doing more meaningful work as engineers, like designing, and then whatever it is that we think is the more meaningful work, right? So anyway, I believe in it, yes, as well. What I'm going to talk about today, some of you may have seen some of this, but this is some research that I did on the Mirai botnet. I'm not in the research function at Radware, but I'm a very technical person, so obviously when this stuff hit the news and hit the networks, we were all over it and wanting to learn more about it. So what we are going to talk about, this is a study of the Mirai structure. This is a study of components in it, attack vectors that are included in the stock attack. So obviously it's been modified many, many times since then, but since it was released. It's focused on the network aspects of the botnet. So me as a network engineer, this was the things that were interesting to me in Mirai. This is not a code review. There's plenty of that out there, and this isn't a how-to guide, how to set this up. But I have this actually set up in my basement, and we were thinking maybe if anybody's interested after this in the social aspect of the night, we could, if anybody wanted to see it in action, we could log in and present it up on the screen and see attacks, that kind of thing. This is not advancing very well, so we'll try this. So we have to kind of start the story off with what happened on September 30th. A threat actor named Anna Senpai released the code for Mirai onto hackforums.net, and Anna Senpai said, you might have heard of these attacks, you might have heard of my botnet, here's the code, I'm getting out of it. I'm getting out of the business, have fun. And Anna Senpai released everything and where you can find everything, right? The bot itself is comprised of a couple different setups. So somebody here, somebody that looks like Heisenberg maybe from Breaking Bad, sets up a CNC server and a scan listen server. And the CNC and the scan listen server, you can automatically start the bot propagation inside of it. So it can go out and just start scanning Telnet, looking for devices, IoT devices that are attached to the network, and start to brute. And then it will find something, right? And then it will ultimately get in, and it will turn into this green circle oval at the bottom. So the bot, once he's infected, he is self-replicating. So he starts to scan other devices. He downloads the code. He starts to scan other devices, and the process continues, right? So just as an animation, from this point, we see the bot has found a new victim. He does it by a Telnet port scan. He does a brute force login of the existing code. The initial code is 61 usernames and passwords, so 61 default credentials in the default code. Finds one. He reports that up to the scan listen server. Scan listen server says, does this guy exist? No, so I now have a loader service where I tell him to download new code, and now we've got a new bot, and then on, the process continues, right? And then there's another aspect. We've got another Heisenberg here who he says, hey, let's make some money doing this. So Heisenberg 1 sells to Heisenberg 2. You can have access into my botnet, and I'll sell it to you for so much money. And it gives him control even over an API, right? So this is a screenshot of the code that shows the default usernames and passwords that are included in the code that's available on GitHub, right? So this is just a blow up of root and a couple different passwords, but there's 61 default ones there in the one that was released by Anna Senpai. There are 11 attack vectors. One of them is blocked out, so really 10 effectively. But what we're going to do here is go through what each of these attack vectors look like. We're going to go through what the payload looks like. We have packet captures and kind of talk about what each one does. This one is really interesting to me. This is the one that was largely involved in the Dyn attacks. The DNS water torture attack, we're going to get into it, but what it does is it creates random queries, basically, for an existing domain that somebody is authoritative for, and he just comes up with, as we'll see, a 12-character string subdomain on an active domain, and he just overruns the server. So we're going to talk about this. This is what was highly involved in the Dyn attack, as well as some other things that there were some SYN flood aspects to it too. So as I'm going through the code, there are a couple interesting things that we found through here. I'm not a code guy, I'm more of a network guy. But this looked interesting to me. This is called a safe string, and there's a URL here. So obviously, being somewhat of a security guy, I go and put this onto a safe machine, and I look this up. It looks like a good URL. I got rickrolled, right? So thank you for that one, Anna Senpai. Another one, this is the prompt here in Russian says, "I love chicken nuggets." You can actually make this say anything you want, but this is what comes in the stock code. So a playful, a playful author of the code, right? So here's my lab setup. So again, as I said, this is in my basement. This is basically everything here. I'll come over here. Everything in this box here is a VM running on an ESXi box. So I have one thing that's a Bastion host. I'm sorry if you guys can't see this too well. I'll get out of the way. From left to right, I've got a Bastion host that he was my utility box. I use him to run screen, to jump into other devices. I used him to serve local files that I wanted, the bot is downloading. It has to download binaries to load onto the infected devices, right? So I'm serving all that stuff locally on util1. NS1, because I wanted this to stay inside of my thing, and a lot of this is based on DNS. So I just have a basic bind machine running DNS to serve DNS locally. I had to make some modifications to the code, which we'll talk about, to get this all to work inside of a closed network. The command and control, the C2 server here, he's a machine in the hypervisor. The scan listen server is another one. And then outside of the box, I wanted to see what would happen with just another server. So I put a Raspberry Pi in there and let him attach to the network and see what he could do. And then so going north and then east, I've got this. This is my attack network, 192.168.3. I've got a Linksys, which we'll talk about why he's there. I have a Shrikam AP003, which is just a $40 IP camera that you can get on Amazon. And I have a Linux box that is my target, right? He's the one who he's running Apache, I'm sending attacks to him, and I've got another interface on him to do packet captures and see what these attacks look like, right? So this is what the lab looked like. It's a little bit different now. But some things that I had to do in the code. The code by default blocks a lot of prefixes. So why is this? A lot of these prefixes were initially unrouted, right? So a lot of them are DoD networks, a lot of them are reserved networks, but you'll see that because I said I'm doing 1918 space, right? So 192.168.2 and 3 are blocked here in code, right? So I had to do some things to get this out of here. Other people have said, why is this, why are these things on here? Well, the answer is, if these prefixes are not routed on the internet, why waste scanning resources on a bot to go ahead and try to brute force IPs that aren't really routed on the internet, right? So anyway, I changed it, and here's how I had to change my code. I had to basically go through and say, each first octet, ignore it until then I drilled down a filter that said, I basically only want you to scan 192.168.3/24. So that's how I did it. So the processes. There are a couple things that we have to start here. We have to manually load the scanner process. This is on the C2, the CNC server, where we basically, after we've loaded the code and compiled it, I start it with mirai.debug.dbg. And here you can see in the green box, among some other codes, well, maybe you can't because it's pretty small, but it says scanner process initialized, scanning started. And here's what it looks like, right? So in my case, this was the CNC-based bot. Remember I said in that diagram from the beginning, you can start this from one artificial bot on the command and control server, right? And he does the scanning. So here you can see, in this case, he was 192.168.2.14, is doing a bunch of port scanning on port 23 to all of these just random IP addresses, right? So ultimately, he's going to find something, and then the process is going to start. So here's a screenshot of what happens when he does that. Now, this is after I've done my trimming this down to my 1/24 that I want to scan. But here's an example of the bot in the scanner finding 192.168.3.2 and trying root and XC3511 as one example, and then guest and 12345 as another username password combo. You might think that this is, maybe it finds an IP address and it attaches onto it, and then it continues to brute and brute and brute. That's not the case. It really is a random, sporadic. It might be 5 minutes before a host gets tried again, right? I don't know the rhyme or reason to it, but just my experience and what I've seen with it. So that's what happens, but perhaps if you have 100,000 bots doing this, maybe you gain some efficiencies again that way. So here's how we start the scan listen process. For my testing, I didn't do too much with this, but this is one of the things that you have to start, right? So this is a separate server. You start scan listen, and he listens on TCP 48101. So the loader is the function that once he's been told to, he will start to begin putting code onto the box that has been identified as vulnerable. One of the things that you can do with this is pipe in a known list of IP addresses and usernames and passwords, so to maybe make the process a little bit faster. I did that, and that's how I'll show you my example. I talked about a linksys. So as I'm thinking about, before I got too deep into this project, I'm thinking, well, Mirai infects BusyBox. I know that some of these old linksys routers run Linux, and sure enough, I grabbed one out of the basement, and it's running BusyBox, so I'm thinking, great, this is going to be easy, right? So I get in here, I find on the web the username and password for the default telnet stuff, and I get in there, and I start to attack him, and it doesn't actually work, right? So the reason that I think this is that there are binaries that are built specifically for the devices that you're trying to attack. And whatever the processor is on this guy, I don't think that there's a binary built for him, so I think that's why he failed. But anyway, so back to the drawing board, right? So I tried a bunch of other things, and then ultimately found this, as I said, Shrikam AP003 that was $40. I went to the list of known devices that were vulnerable, and I ultimately got him, right? So you might not be able to see this, but the slides will be available if you want to see it later. I do just a quick nmap of him, and I see that 23, so telnet's open. Actually, asterisk is running on here too. I have no idea why. And TCP81 is open. So I try to telnet into him, and I use my usernames and passwords, and it works, right? So I get in. So great. So here's where I use that, back to the loader. I used the loader with a forced list of usernames and password that I wanted to attack, because I didn't want to wait for the scanner process to go through everything and find something vulnerable and try something and try it 5 minutes later and again and again. So on the top of here, you might be able to see that we can, I'm catting a list of IP addresses. That list of IP addresses has a username and a password, and you could add a switch of what kind of processor it is, and then I pipe in the loader, right? So what we're seeing here in these green boxes is that I go from no logins to 1 login, and I go from 0 TFTPs to 1 TFTP. One thing that I ran into here is that originally I thought this would just do a wget to download everything, and I had to actually do packet captures to see what was happening, to see that it's also trying to TFTP. You know, it was trying TFTP instead of wget. So ultimately I had to do it through TFTP. Apparently it can do it with wget as well. But if this were the active running loader, you might see 10,000 logins and 40,000 processes or something like that, right? So this is just my closed lab setup. And then the new bot that I have infected, he starts his propagation as well, right? So we've got a source IP of 192.168.3.140, and he's starting his port scanning of all of these random IP addresses. All of these are on the switch that I had at the time. Then one of the things I did this past week was put them on a new switch. But so here we can see the 80,000 bits per second of just scanning traffic. So he's doing 80K of just trying to find somebody to attack, right? One thing that we saw, Mirai is very predatory. So once it goes in and finds a box to attack, it shuts down Telnet. One thing that is very interesting to me, though, is that SSH was opened on this one camera after I shut down Telnet. The bot doesn't do that. I don't know why. The only thing that I can think of is maybe my camera was doing some kind of watchdog process that said, if Telnet's gone, maybe start SSH or something. I don't know. But that's not what I was after. I just thought it was interesting that Telnet is gone, and now SSH is open. So the attacks. These are the attacks that are in there. Some of them are unique. Some of them are things we've all seen before. But basically, we've got a version of the UDP flood. We've got a version of a SYN flood, ACK floods, the TCP stomp flood, which is a pretty cool one we'll talk a lot about, a plain UDP flood, valve source engine flood. There's a DNS, which is the DNS water torture attack that we talked about with Dyn. There are two versions of GRE attacks, and then there's an HTTP flood. I don't want to get too dry here. I know everybody's had long days, so we'll kind of pick the interesting parts out of here. The UDP flood, so it's a UDP flood. We've got a random source IP, random destination IP. I'm sorry, random source port, random destination port. This is different, though, from the traditional tools that are out there, like HOIC and LOIC and a lot of these DDoS as a service things, where a lot of you often have a commonality in the fingerprint of the attack. So there's often a common source port, or often a combination, or often a common destination port. If I'm receiving this attack and it's 30 gig of attack here, what am I going to do except block all UDP, right? Because I can't find a common source, I can't find a common destination. That's going to be harder to do on a router ACL or a firewall filter, right? But in this example, I had just about 20 meg of traffic out of just this one camera. No, just about 2 meg. This is what it looks like in TCP dumps or in Wireshark. So again, it's just random source port, random destination port. Kind of hard to block unless, if you can block all UDP, then that's the way to do it, right? And then after this attack, the camera crashed. And sometimes it does it, and sometimes it does not do it. So I've since got another camera, and both of them kind of exhibit that behavior. They just kind of crash sometimes, and when they crash, they reboot. And when they reboot, the code is flushed, right? So then we got to start the loader process all over again. That's kind of fortunate for a lot of people. Like, I think with Deutsche Telekom, their routers, they were able to just reboot them after their infection, and they didn't lose 900,000 routers at customer edge. The SYN flood attack, random source port, random destination port, one-to-one correlation. Again, the randomness here in each packet makes it a little bit difficult. You could potentially do some stuff with blocking just on the TCP flags. Here's what it looks like in Wireshark. The ACK flood, same kind of thing, random source port, random destination port. The host replies with a reset, so there's a one-to-one correlation. That can get it to be a tricky thing for the actual host itself, because the host is replying. There's CPU process that's going along with this as well. The stomp flood is a really good one. So I couldn't actually run this on the one camera that I had at the time. So this is an example of in terms of packets per second and bits per second. This is coming from the Raspberry Pi that I was talking about. But I don't think that was a fair analysis because it has more compute, right? It's a bigger box. But anyway, the stomp flood is the classic ACK flood with a twist. So he'll set up a session. Session will be established. I've got a sequence number, right? So I've got a fully established session. Here's a good example of it. So I've got a fully established session, and then he starts with, once the session is set up, then he starts an ACK flood. is designed to defeat a lot of DDoS mitigation things, because now I've got already a whitelisted session, basically, and then he comes with an ACK flood. So what's interesting here, though, is that there's maybe a flaw in the original code, because what happens is you might be able to see we start on port 42924, and that's just a random thing, right? Then once the session is established, I switch to a new port, 40933, and I'm including my session ID, and I'm including a lot of the same information, but what's actually happening here is some DDoS mitigation appliances, like maybe the company I work for, are going to see this as an out-of-state attack and then be able to block it that way, right? So, but the code is very variable and modifiable, so I wouldn't rely on that to be the only method of blocking it, right? But it's a very interesting one because it's designed to beat DDoS mitigation appliances. The UDP flood is a high-rate UDP. It says that it's random, but I only saw it with a destination port of 54005. So if you see 54005 in your network, it's a good indicator that it's coming from Mirai, and you're lucky because you can probably block UDP 54005, right? 20 meg, though, out of that attack, out of one single camera, so not too bad. That's what it looks like as a TCP dump. The Valve source engine flood. So Valve is a company that makes software that relates to gaming. And the source engine flood is an attack specifically on that. So it's a UDP flood, random source flood. Because it's attacking Valve source engine, it's going to be on port 27015. And this is used in a lot of the streaming gaming stuff like Half-Life and Counter-Strike, right? It's interesting. It's I mean, you can see it here in a packet capture, but it's interesting that it's 27015. So if you're not running this in your network, you can block it easily. If you are running this in your network, I don't have the answer, right? The DNS resolver. So this is a really good one, and if we want, I'll show examples of this afterwards. If we want to play around with the lab in real time after everybody's broken for beverages and snacks. But here's what it looks like as you launch it in the console, right? So I'm saying I want the DNS attack. I'm saying I want the IP address that I'm attacking and the duration, and then I actually have to include a domain name that I want to, because it's a that I want to attack because it's a DNS attack, right? So it turns out that the IP address doesn't really matter, because all that's going to really happen is the bot that is infected is going to ask his DNS resolvers, how do I find abc1234556.domain.com, right? The payload looks like is it's a 12-character string .domain.com. So you probably can't see this, but the interesting point here is that my camera received this, received 192.168.3.2 from the DHCP server as his DNS resolver, right? So what's happening is the attack is actually coming from real DNS servers. No matter, even if it's sourced from a camera, the attack is coming from real legitimate DNS servers. The reason this is a problem is you can't block Verizon DNS resolvers and Comcast DNS resolvers in your network, right? So you have to have a different way to handle this. This makes it very interesting to try and attack. These attacks themselves, when I was at Server Central, we would deal with these. They're very high packet per second, high bandwidth attacks. So we had one that was 25 gig of bandwidth, but it was 50 million packets per second. So that's almost 10, if a 10 gig interface has about 12 million packets per second of line rate, it's about 5 10 gig links of capacity filled with half of its bits per second capacity, right? So that could be the reason if you see that happen. Here's what it looks like. So it really didn't matter what I put in for the parameters of the domain. It always just appended a subdomain of 12 random characters dot whatever you put in dot domain, right? The GRE, bless you, Jess. GRE IP flood is pretty cool. This, as the Mirai stuff was really happening, Arbor reported as the Olympics were happening, hey, we're seeing a lot of these GRE attacks. And ultimately, we found out later that these were coming from Mirai. But what was interesting about GRE is it's the highest packet per second, highest bandwidth attack available in the tool. So suddenly, it makes sense why people would be using GRE flooding out of Mirai, right? It's the most efficient attack in the tool set. What you're going to see if this comes into your network, you're going to see a tunneled source IP of this IP address. Again, it's high bit per second, high packet per second. Some of these parameters that are in here for options don't actually work, and I found that with a couple of the other tools as well, right? So they don't all work, but it is still highly customizable for an attack tool. You get a random, let's see. You get a random source IP address and destination IP address that is tunneled in the tunneled traffic too. So, I don't know, it's pretty interesting, pretty efficient. Here's an example of what each one of those, the encapsulated and then the outer frames look like. A similar attack with GRE Ethernet flood, which I thought was very cool. Same concept, still high packet per second, not as high, but random source MAC address and random destination MAC address tunneled inside of the payload. I thought that was, I don't know the reason why that would be included. Maybe if any of you do, could think of a reason that would be included. It's interesting to me, but I don't know the effectiveness of it or why it would be useful. Here's what it looks like in Wireshark and TCP dump. And then the HTTP flood is a pretty good one. All it is a get/slash attack, but what I was finding is that the machine that I was attacking was just a regular Ubuntu machine running Apache 2 with a it worked page, right? Just the basic page. So the bot generates 500K of gets, but the web server that is just running a basic splash landing page is returning 12.5 meg of traffic back to me with one bot. And that was really interesting to me. So if I have 100 bots doing this, I've got a huge, amplification factor in the attack that I'm applying to these boxes, right? So that was very interesting to me. So that's what it looks like. Here's the decoding of it. But it's really just the it worked page. So the bot also includes 5 user agents. So you could see some of these real, these might look like they're real. I thought that this was creative to have 5 of these in here, real browsers. One thing I want to talk about, so we're seeing on this Mirai attacks Twitter feed a lot of things that are 60 seconds, right? 30-second attacks. And it could be people just playing with them. But when I was working with Alex, at Server Central and at NLayer, we would see these attacks that were 30-second attacks, right? And they're hard to kind of fingerprint because if you're polling them, if you're doing SNMP polling, how are you going to find these really? SNMP polling, you're going to maybe catch them, maybe not catch them. If there's 30-second bursts that are 10 gig bursts, they're probably going to fall outside of your SNMP polling interval. So they're going to manifest as either complaining of, hey, network guys, the network's not working, or maybe they'll show up as output drops on switch ports, right? But something's going to be hard to find. So, you'll want a tool here, an appliance on site or NetFlow, something like that to help you identify some of these attacks that are anomalies, right? There are variations to the code. This was just in December, so I know we're a little bit farther now, but by December there were 53 variants of Mirai that were released by December 9th. So people are taking with this and running with it. And what's so interesting is that there's especially on hackforums.net, you'll see people are asking for help, and some people are breaking their chops about it, and some people are actually helping them. So we have widely documented, this is like the open source botnet, right? It's a celebrity botnet. It's not the only one. We're going to talk about a couple of them, but it's definitely capable of some damage. We talked about what happened with Deutsche Telekom, how that was changed to TR069, so using Mirai to infect the Deutsche Telekom home CPE routers for people on their network. So almost 1 million routers there were infected and then luckily recovered. And then something else, I won't touch on this too much, but we're seeing a domain generation algorithm as well. So we see this in malware too. You know, it's a common thing in malware, but we're seeing this for the domain generation algorithm aspects of this for the calling home or the calling to the command and control, the C2 servers. So interesting that this stuff is happening. That's just an example of them. So how can I catch this in my network? Well, traditionally, the command and control, the C2 stuff is on TCP/23, so Telnet. So if you see a lot of Telnet, listen, we probably don't run too much Telnet in our networks anymore, right? So if you're seeing a spike of that, that could be a reason. Replication is also on Telnet and 2323. Scan listen server is running by default on port 48101, so if you're seeing that in flow data, that's a good way. Honeypots we'll talk about, and scanners. Here's a honeypot that I played with a little bit, released by Symmetria. So here's basically the code. All you have to do this on Ubuntu to install it. Here's what it looks like. So it's basically listening for people to connect to it. It's listening on Telnet and waiting for commands to be issued, and then it will basically report on them. It won't issue the commands. My colleague in the EMEA region is building one of these for Hajime as well. Well, good transition. Hajime is the next up-and-coming threat for botnets, right? So he's got a pretty cool one that he set up for Hajime that is tracking that. But again, I say that Mirai is kind of the celebrity botnet, but it's not the only one that's out there. It's just the first open source one that we all have access to that is so damaging as well, right? So Mirai, Hajime, Adra, and Bashlight are the big ones that people are talking about right now, and these are links to how to find them. And then the last slide that I have here, you know, people are arguing about, is Mirai still a threat to us? I think it is. I think that people also are saying that, you know, because so many people are running it, that, you know, once a device is rebooted, he can be then overtaken by somebody else. So I was at a conference last week where people say that the Mirai traffic seems to be lower, but I don't think that that means that the threat is diminishing, right? I just think that there are smaller botnets that are now controlled by more and more people, right? It is a game changer. We saw that, you know, obviously with what happened with our friends at Dyn. We need to be mindful of what's happening in our networks, and we also have to give thought to how to fight this. I have some personal ideas. I think that the service providers are the best people suited to fight this attack. That's not a popular idea, especially in the service provider market, but these are the people who, you know, the end users can't be responsible to troubleshoot the Mirai, and you could argue whether or not the manufacturers should be accountable for this. I think they should too, but really the service providers are the people with the flow data and the ability to fingerprint this stuff in their network, and then, you know, do something about it. Put the customer in a penalty box, or, you know, help them to block it. But each one of those, every time there's a call to a customer, there's a cost associated with it too, right? So, so that's it. I appreciate your time. If you have any questions, I'm here. My friend Jake's here as well in the back, and you know, we can. If anybody's interested, I'd be happy to dig into real-time stuff in the lab at home too. So, thank you very much.
It's question and answer time. Do I hear any questions from the floor for Ron? Let me come over with the mic.
That was a great presentation.
Thank you.
A quick question. How long did it take for you to set up your lab?
A lot of learning. So.
How long did it take?
So, well, that's the thing. I mean, it took a lot of. It wasn't okay. It took longer than I thought it would, because it does have the reputation of anybody can set it up, and especially on that hack forums, if you can't set it up, you're a skid, and you know, this is like a lot of like insulting that, you know, so. It took longer than I thought, and it took longer than I thought to figure out things like, why isn't my scanning working? Oh, because 1918 space is excluded from scanner.c, right? So there are things that was a lot of discovery work. It probably took a week of solid work on it I'm not a coder, so you know maybe
That was very thorough. I was very impressed.
Yeah. All right. Thank you.
Anybody else? Any more questions for Ron?
One here, Alex.
Actually, I do have two of them, unrelated. The first one is, actually they are sort of related. First one is the initial botnet script. Is that in C or C++?
So I think that there's C, and then part of it is written in Go. I have actually the people who do the code analysis. I have what that is. So I know that it's C, and it's also in Go. Half of it's Go, half of it's C.
Okay, so the second
but I can
part,
find out for sure for you.
the second part was the actual packet crafting, and this was going back to the how you're able to get more throughput with the GRE attacks.
Yeah.
Maybe the packet crafting is more efficient for the GRE. Do you know the library that the packet crafting used?
No, I don't. But there are things that are tunable in it as well. I didn't really touch on the fact how you can set the packet length for each one too. So it would get bigger than that, but I don't know I'm not, like I say, I'm not a programmer or like I'm not that level of a network guy, so I don't know the libraries that were used.
Right.
Yeah.
It's actually interesting to see how easy it was to set up the honeypot. That's a Python library?
Yeah, and so that may have, for a while, it had an issue where it would crash after some time or so many connections. It may have been updated since then. I haven't looked at it, but that's all it takes to set it up. There's another one. So that one's called empty pot, like MT pot, but empty, like, you know, easy way to remember it. Yeah, right. Yeah. Let's see. There was another one. I forget, that was a completely different thing. That was, you would just bring it in through Docker and it would run by itself. But that one served my needs. Yeah. Yeah. Thank you. Yes. Uh-huh.
They were able to poison, do a DNS poisoning for the ISP.
I don't know.
No, I already finished.
Yeah, so the question was, with the DNS attacks that happened, was somebody able to do DNS poisoning in the ISP recursive resolvers, right? So I don't think that that's what happened. I think that really somebody is in the command and control saying, give me random string.joespizza.com. That doesn't exist, right? So the resolvers don't have a cache for it, so they ultimately have to go through the hierarchy of DNS to get to the authoritative name server who's going to say, give me what you've got for abc123.joespizza.com, and it's not going to exist, right? So that itself is a little bit, you know, there's an impact on DNS servers if they don't have it cached. We have performance drop once it has to look things up, but it's also 400,000 requests coming at once or whatever the number is, so easily able to overwhelm just compute infrastructure, right? Yeah, so I don't think that's a good question. I don't think that it was a poisoning thing. I think that it was just, it was legitimate DNS queries for fake subdomains.
Flush.
The question is, why did the IoT boxes shut themselves down and flush? Why is Mirai flushed from code? I think Mirai is flushed from code as to not leave a trace that it existed. But I don't know that that happens with every variant of it. I think that it's probably more attractive to have the code not be flushed. But what happens is it's loaded onto the box, and then it deletes all of the file structure that exists to hide it on the local box. So it's just running in memory at that point. But then once memory is flushed, then we lose everything, right? So it's to avoid detection, but you know, I don't know that that's how it was written. You know, I don't know that that's the most efficient way to do it.
Any other questions?
Yeah.
This.
Yeah. Question is, how did we get to reproduce it? So basically, you can download this in GitHub, and I basically set it up in VMs that were on a VMware box that I have at the house. And then I ultimately bought 2 cameras off of Amazon to infect and use them in my testing. So it's now the switch that I replaced is a Juniper EX that is running a whole lot louder, and my wife is noticing the loud noise that's running, and my kids are saying, what's running in the basement, right? So it's really just, it's just basic network stuff that is running in my basement. Yeah. So Kali Linux, have we used Kali Linux? It's Kali Linux is like a test tool. You know what's? Oh yeah, because it's being recorded.
Okay, my question was, have you used Kali Linux in your lab configuration?
I did, yeah. So actually the first...
Because I don't see it. I just saw a bunch of Ubuntu.
Yeah. So first, I started with... I actually started with Kali installs of this, and I found that the overhead wasn't necessary, but Kali's based on Debian. Most of what I did on here were Debian boxes, and then like the command and control boxes were Debian boxes, and then Ubuntu is just my favorite OS, so that's what I used for the things that didn't need specific, you know, that it didn't need to be just flat out Debian.
Okay. In this specific case, what do you think the payload was? What was the intention behind that payload?
The Mirai attack?
Yeah.
Or the Dyn attack?
Yeah, the Mirai.
So I don't know. I mean, we used to see them at Server Central all the time. So I just think that I asked so I was at a conference last week, the Microsoft Digital Crimes Conference, and one of the guys gave their analysis of what happened. So I asked him. I said, "These DNS water torture attacks are not new. What was the change here?" And he said that it was that combined with the way that a SYN flood came in. You know, I don't know that that's exactly why or what happened, but it was enough to break them. And these water torture attacks are not new. Like we used to handle them at Server Central, you know, for years. So.
Thank you.
Yeah. Thank you very much. Thank you.
Anybody else for questions before we go back? Going once? Going twice? Can we have a big round of applause for Ron?
All right. Thank you so much.
Thank you for coming out and making this such a success. There's more to eat, more to drink. Go network, networkers.